So in the previous class, so we had discussed about the stereochemical aspects, right? So we have discussed about the stereochemical aspects in the previous class. So we have seen the different terms, okay, which are involved during the stereochemistry. So what we have studied in stereochemical aspects, that how are the spatial arrangement of the atoms, okay, different atoms around the carbon in the tetrahedral when the molecule is in tetrahedral manner, right? So we have studied what is chirality. So what is chirality? Then we have discussed the other terms like optical activity, right? Then optical isomerism, mesocompounds, then what are enantiomers. Then we have discussed about what are dextro and levorotatory systems. Right. Then we have discussed about what is retention of configuration. What do you mean by inversion of configuration? Then what is racemic mixture? So I have told you what all are the important things, right? So what is asked? So all the important things we have discussed. Then we have studied the stereochemical aspects. Okay, how stereochemically like how the SN1 mechanism undergoes via the stereochemical aspects, as well as the SN2 mechanism, right? So in SN1, the attack can takes place from front also and from behind. The possibility is it can have a retention of configuration and 50% inversion of configuration. So it is said to be having a racemic mixture, right? And similarly, when we proceed via SN2 mechanism, okay, when we have a SN2 mechanism, that is when we are discussing about the stereochemical aspect of SN2 mechanism, we know that the attack of the nucleophile takes place from the rear end. Okay, it takes place from the rear end, that is from the backside. Okay, so what is possible? 100% inverted product, whatever the product obtained, okay, whatever the product which we obtain, it is 100% inverted. Okay, we have a 100% inverted product, and thus this type of inversion is called as what? It is called as Walden inversion. Okay, mark this as important. So in SN2 mechanism, what type of inversion is seen? It is a Walden inversion. Okay. Then we had also discussed the differences between SN1 and SN2 mechanism. So today we are going to continue with the remaining reactions. Okay. So the first is the elimination reaction. So what do you mean by elimination reaction? Elimination means removal. Okay, elimination. How we eliminate? It is a removal of some atoms. Okay, so here it is undergoing a dehydrohalogenation. What do you mean by dehydrohalogenation, students? So hydro means hydrogen. Okay, removal of one hydrogen and one halide. Okay, so removal of one hydrogen and one halide. It is called as what? Dehydrohalogenation. Okay, so what is this dehydrohalogenation? So dehydrohalogenation, it is a beta elimination. Now what do you mean by beta elimination? Beta elimination means at the beta carbon, okay, at the beta carbon there is a you can see, so this is your beta carbon. Okay, so when your hydrogen is attached here, so okay, so hydrogen is, so this is your alpha carbon and this is your beta carbon and this is your beta carbon. Okay, so there are two beta carbons. So the halide to which the carbon is attached, so that is your alpha carbon, and the next two are your beta carbons. Okay, so at this beta carbon, what will happen? There will be elimination. Okay, there will be removal. Okay, there will be removal of a hydrogen and one halide. Okay, so what is happening? So this is so here you can see there are two carbon atoms. Okay, there are two carbon atoms. So from where to remove the hydrogen? Okay, so from where to remove the hydrogen? So this follows one rule which is called as the Setzeff rule. So what is the rule? What is the name of the rule? It is a Setzeff rule. Okay, so it will follow Setzeff rule. So let us see what is Setzeff rule. So when a alkyl halide, so this is the alkyl halide, you can see here, right, students? So this is a alkyl halide. Alkyl halide means what? Yes, RX, right? So R can be your any alkyl change. So we have seen what are the different alkyl chains, right? So methyl, butyl, okay, propyl, ethyl. So so this can be your any alkyl chain and a halide group. So when a alkyl halide, okay, so when you have a alkyl halide, so suppose I take a generally, okay, if I take generally, so like this. So let me represent the alkyl halide. So this is your alkyl halide. Okay. And I react this alkyl halide. Okay. Now this alkyl halide is containing a beta carbon. So this is a alpha carbon. How do you understand it is alpha carbon? So the halide to which the carbon is attached, it is your alpha. And the next carbon, okay, next carbon to the alpha is your beta. Followed by, then it will be gamma, delta. Okay. So this is the alpha carbon, this is a beta carbon. So first carbon is termed as alpha, the second carbon is termed as beta. Okay. Now this alkyl halide, it is treated, we are going to treat it with alcoholic KOH. Okay, what do you mean by KOH? KOH is a potassium hydroxide. Okay, KOH is potassium hydroxide. It is a strong base. Okay. And how we have prepared this KOH? We have prepared this KOH in alcohol. Okay, we have not prepared in water. We have prepared in an alcohol. So it is called as alcoholic KOH. And what we are going to do? We are going to heat it. Okay, we are going to heat it. When you heat this, when you heat this alkyl halide with alcoholic KOH, what is happening? So your one halogen, one hydrogen and one halide is being removed, and what you obtain is you obtain one alkene. Okay, you obtained one alkene. So this is the elimination reaction with the removal of one K and X. Okay, and one water molecule is eliminated. So this is an example of a elimination reaction. So from a beta carbon, your hydrogen is removed, and from your alpha, your halide is removed. So this undergoes a beta elimination, because at beta, at beta position, what is present at beta position? Your hydrogen is present. Okay, so it is undergoing what? Beta elimination. Now here, so when you see, so what does Sedzeff rule states that? So now when you see this example, okay, so this is a halide and to which the carbon is attached, this is a alpha carbon and this is a beta carbon and this is a beta carbon. Now, what is the possibility from which the hydrogen should be removed? So the Sedzeff rule says that, okay, Sedzeff rule says that if a haloalkane, okay, if a haloalkane contains more than one beta hydrogen atoms, if it contains more than one beta hydrogen atom, then elimination will take place according to Sedzeff rule. And what is Sedzeff rule? Okay, so it can eliminate a molecule of hydrogen halide. So elimination of hydrogen halide, okay, the hydrogen will be removed. Okay, hydrogen will be removed from the this, okay, which is highly substituted, okay, which is highly substituted. So alkene, the highly substituted alkene. Now here, so here you can see, so from this, so this is a highly substituted, so this is one carbon, okay, one alkyl group, and here is another alkyl group, so which is highly substituted, this particular group. Okay, this is a ethyl chain like. So this will give you a major product and another. So if you remove the hydrogen from this beta carbon, then that will be a minor product. So this is a Sedzeff rule. So if a haloalkane can eliminate a molecule of hydrogen in more than one way, then the preferred alkane is one which is more highly substituted. Okay. And now one more example. So you have to tell me the answer for this. So suppose CH3, CH2, CH2, CH, okay, Br and CH3. So what is this molecule? Yes, so it is a 2-bromobutane. Is it? 1, 2, 3, 4, 5. So it is a 2-bromopentane. Okay, 2-bromopentane, right? Now, if I react it with alcoholic KOH, okay, can you tell me the product? What will be the preferred product obtained? So this is a alpha carbon, this is a beta carbon, and this is also a beta carbon. So according to Sedzeff rule, yes, which is the product obtained? So it will be what? So CH3, okay, CH2, CH, double bond, CH, CH3. Okay, so from this hydrogen will be eliminated and this. So a double bond will be formed. So this is one product, which is a major product. Okay, this is a major product. So let me write it more clearly. So this is CH. Okay. So this is the then one more product is what? Here also it is possible. So it is CH3, CH2, CH2, CH double bond, CH2. So this is a minor product. Okay, and this is a major product. Fine. So this is your Sedzeff rule. Okay, this is your Sedzeff rule. So what is the name of this first product obtained? Yes, students. What is the name? Can you name it? So you have to see that the double bond gets a piece number. So 1, 2, 3, 4, 5. So I'll give the numbering. You please tell me the name.
Pentatohene.
Okay, pentoene, good. And the minor product, it is pent.
Pent-1-hene.
Yes, pent 1E. Okay, so major product. So this is your Sedzer fruit. So what is the ease? How you can remove the how it undergoes dehydrohalogenation among the halides. Okay, so tertiary alkyl halides are more stable, then secondary, and then your primary. So this is the ease of removal of the dehydrohalogenation. So this is the particular reaction. So elimination reaction. If you have more than one beta carbon, then you have to follow which rule? Sedzeff rule. Sedzeff rule states what? The product form. Okay, the removal of hydrogen will be from the more substituted alkene. Okay, the product form will be a more substituted alkene like that. So this is the elimination reaction. Let us go for the next one. Okay. So next is the reaction with metals. Okay. Reaction with metals. So there are different alkyl halides. Okay. Different alkyl halides, like your halides can be your chlorides. Okay. Then you can have your iodides. Then you can have your bromides. Right. So different alkyl halides. Okay. Different alkyl halides like the chlorides, iodides, or alkyl bromides, they will react with active metals. Okay, which are the active metals? So active metals like sodium, magnesium, lithium, cadmium. Okay, and they will give you a carbon metal bond. Okay, what type of compound they form? They form a compound, and these compounds, they are termed as carbon metal compounds, and these are called as organometallic compounds. So organometallic compound. So whenever a carbon and metal bond is formed, okay, remember that. Okay, whenever a carbon and metal bond is formed, what are the name of that compound? They are called as organometallic compounds. Okay, so whenever alkyl halides, okay, whenever the alkyl halide, different alkyl halides, when they react with active metals like the sodium, magnesium, lithium, or cadmium, okay, they form a type of bond, okay, or they form a type of compound where you have a carbon and metal bond, okay. And these compounds are called as organo. Why? Because carbon compounds are called as what? Organic compounds, right? So organometallic compounds. Okay. So let us see first reaction with Mg. So let us see the third one first. So reaction with Mg. So alkyl halide. So this is what? It is a ethyl bromide. So ethyl bromide. So let me take the example in general. So if I take alkyl halide, so it will be Rx. So if I take any alkyl halide, okay. So this will be example. So alkyl halide, if you treat it with Mg, okay, if you treat it with active metal like magnesium in the presence of dry ether, okay, what will be the product form, students? What will be the product obtained? It will be RMgX. Okay, it will be RMgX. So this is called as Grignard reagent. What it is called as? Grignard's reagent. So what is Grignard reagent? So Grignard, important, please make a note. What is Grignard reagent? So Grignard reagent, it is a organometallic compound. Okay, what is Grignard reagent? Grignard reagent is a organometallic compound, and how they are obtained? They are obtained by reacting your alkyl halide with active metals like magnesium in the presence of dry ether gives you RMgX. What is RMgX? RMgX is Grignard reagent. Is it clear? Yes. So one example here it is given above. Okay, ethyl bromide plus Mg in the presence of dry ether. Okay, ethyl in the presence of dry ether gives you ethyl magnesium bromide. What it gives you? Ethyl magnesium bromide. Okay, C2 that is C2H5 MgBr. That is here. This is your R. This is your Mg and this is your X. Is it so? Right? This is your Grignard reagent. So this is the first reaction. So reaction with metals, active metals. Okay, this is Grignard reagent. So mark this as important. Okay, it is a alkyl magnesium halide. Okay, so what it forms? It forms alkyl magnesium halide. So this is alkyl magnesium halide. It is also called as Grignard reagent. Okay, halide. Okay, so let us go for the next one. Okay, next is the first one, Woods reaction. Let us study the Woods reaction. So in this Woods reaction, we are reacting the alkyl halide. Okay, we are reacting what? We are reacting the alkyl halide with what? We are, see here, we are reacting the alkyl halide. So let me clear this. So we have seen third one now. So we are seeing now first one. Okay. So what we are doing now? We are reacting the Okay, so here we are reacting the alkyl halides, okay, with sodium metal. Okay, so alkyl halide with sodium metal in the presence of what? In the presence of dry ether. Okay, in the presence of dry ether. And what you will get? You will get, so you have to take 2 moles. Okay, you have to take 2 moles of Rx. What will be the product obtained? It will be RR plus 2NaX. Yes. Hmm. Fine. So this is the Woods reaction. So this name reaction is called as a Woods reaction. What we are taking? We are taking 2 moles of, okay, here you can see, okay, they have written 2 separately. So Rx and Rx, okay. So we are taking 2 moles of alkyl halide. We are reacting with the active metal like sodium. Okay, in the presence of dry ether, we yield a higher alkane. Higher alkane because you can see here only one carbon atom is there. Here you can see 2 carbon atoms. So we are yielding a higher alkane and 2NaX. Okay, so this is Woods reaction. Very important name reaction. Please mark is important. So all these name reactions are very important. So please mark it important. So let us take an example. I want the, okay, I want the, okay, tell me the product now. Example of Woods reaction. Yes, tell me the product. Students, what will be the product obtained?
2C2H5, 2-ethyl,
Just a second. What happened? C?
2C2H5
Hmm.
plus 2NaBr.
Okay. What you have to tell is like this. Okay. So just yes, to NABR, how I'll tell you, see here. This will, okay, to NABR and it will be C2H5, C2H5. Okay. So this is the, that is your N-butane. This is what? N-butane. So the name of the compound is N-butane. So ethyl bromide, okay, sodium, and this is again ethyl bromide. So when 2 moles of ethyl bromide reacts with dry ether in the presence of dry ether, Okay, gives you N-butane. One more, CH3Br, will take Cl. CH3Cl plus 2Na plus ClCH3 in the presence of dry ether. Yes.
CH3 to CH3 CH3
Huh.
2
Plus,
NaCl plus 2
yes.
NaCl.
Yes, so this will be the product of it. Understood? So very important, Wood's reaction. So they can ask you, what is Wood's reaction, or explain Wood's reaction with general equation or maybe with an example. So you have to know that. Okay. So haloalkanes, when they react with sodium metal in the presence of dry ether to give you higher hydrocarbons, this reaction is called as what? This reaction is called as Wood's reaction. Okay, this reaction is called as Wood's reaction. So like this. Fine. Then the next reaction. So this is Wood's fatigue reaction. This comes under, so till now, whatever we have studied, these are the reactions with haloalkanes. Okay, still we are studying about haloalkanes. Okay, we have not completed haloalkanes. So we are discussing haloalkanes. So this is about haloarenes. So let us take this with haloarenes only, Wood's fatigue reaction. Okay. Now next is, okay, physical properties of aryl halides. Okay, so aryl halides, they are colorless liquids or colorless solids with characteristic odor. Boiling point, what happens to boiling point? They generally increase with increase in the size of aryl group or halogen atom. So boiling point, as the, so iodine is higher, it is having a higher atomic mass. Okay, so it will be having more, then bromine, then chloro, and then your fluorine. So this is the boiling point. So as the mass increases, the boiling point also increases. Then the melting point of para isomer is more as compared to ortho and meta, because in para, okay, when we are discussing the para isomer, okay, now ortho means what? Ortho is like the substituted. Okay, now suppose this is your ortho substituted. Okay, then your para is like this, para substituted. Okay, and let me take your, shall I take, okay, CH3. Okay, CH3. Then this is what? CH3, and this is your X, sorry, this is your meta. Let me take a meta. Okay, so this is your meta substituted. So what is happening here? So this is your ortho substituted, para substituted, and this is your meta substituted. So when you see the symmetry, here one atom is present here. So there is no symmetry present. But when you see this para, okay, when you see this para here, okay, so the number of atoms on either side is the same. Okay, if you put a plane of symmetry here. So what is happening? So it is symmetric in nature. So para isomer is symmetric in nature as compared to ortho and para. Okay, here one X is there, here no, right? So because of this, the melting point will differ in ortho and meta position, but para is more symmetrical. Okay, melting point of para is more as compared to ortho and meta. Then, due to the resonance in chlorobenzene, CCl bond is shorter and hence its dipole moment is less than that of cyclohexyl chloride. Okay, so these are some of the physical properties. Then now we are going to start with the reactions of the haloarenes. Okay, what are the different chemical properties of haloarenes? So in this only we are going to, so I know we have to study Wood's fatigue reaction. Okay, with Wood's fatigue reaction, it comes in your haloarenes. Okay, I'll write it here. So we'll remember that. So first one is, so what all reactions we are going to see, okay, of haloarenes. That is nucleophilic substitution reaction. Then we are going to see electrophilic substitution reaction. Then we are going to see reaction with metals. Okay. Now what are the nucleophilic substitution reaction? So as aryl halides, okay, haloarenes or the aryl halides. Haloarenes means what? Okay, these are the haloarenes. Okay, so these haloarenes, they are less reactive. These are less reactive towards the nucleophilic substitution reaction. So what are the reasons? The first reason is due to the resonance. Due to the resonance. Okay, so due to resonance, if we see the resonance structures, okay, of the carbon that is alkyl halide, you can see that the CCl bond is partial double bond character. Okay, it will have a partial double bond character. So as a result, what will happen? The cleavage, okay, the bond cleavage in haloarenes is difficult. So when you have a double bond character, okay, what will happen if you have a double bond character? So let me write the resonant bonds. Okay, so the point will come here. So here you can see that it is having a resonance. Okay, now this will move here, this will move here. So now, okay, so this will move here, this will move. Okay, so these are the resonance characters. So when we write the resonance structure, you can see that the CCl bond, this is the CCl bond. Okay, so this is a C and this is a Cl bond. So this CCl bond, what is that? It has a double bond character and it is very difficult to break this bond. So the cleavage, the breaking of this bond is very difficult. So because of that, the aryl halides, these are less reactive towards nucleophilic substitution reaction. So this is the first point. Clear? Okay. Then the second is what? The difference in hybridization of carbon in CX bond. Okay. When you see the hybridization, okay. So this is what? This is a sp2 hybridized. Okay. And when you see alkyl halides, okay. So this is what? This is sp3 hybridization. So due to the difference in hybridization, okay. So also the aryl halides are less reactive. So as you see, the aryl halides, okay, they are having sp2 hybridized carbon and sp2 hybridized carbon, it is having greater s character and therefore it is having more electronegative. And what it will do, it will tend to hold the electron pair, okay, more tightly. The CX bond electron pair is holded more tightly, thus it is very okay tightly as compared to the sp3 bond. Okay, in rx bond, here the CX bond, the electrons are holded more tightly and thus it is very difficult to break this CX bond as compared to that in the haloalkanes. Okay, so this is another reason, because of the character of this what, the hybridization of the carbon, okay, in aryl halides. So this is the second reason why it is less reactive. Okay, why it is less reactive. So this is another reason. Then next is instability of phenyl carbocation. What do you mean by instability of phenyl carbocation? Yes. So in haloarkane, okay, in haloarenes, the phenyl carbocation formed as a result of self-ionization will not be satisfied by resonance. So in haloarenes, okay, in haloarenes, if the phenyl carbocation, whatever is formed, okay, so this phenyl carbocation, it cannot be stabilized by resonance. Okay, so SN1 mechanism is ruled out. So because of this, so this is another reason why aryl halides are less reactive and they do not undergo, they are less reactive towards a nucleophilic substitution reaction. So this is a compulsory asked question. Okay, very important asked question. Why aryl halides are less reactive towards nucleophilic substitution reaction? Important for 3 marks. Okay, important for 3 marks. So you have to explain this with the structure. Now for example, the first one, due to resonance. So you have to explain the point why due to resonance and you have to write the resonance structures. Okay. Then stabilization by the delocalization of electron. That is difference in the hybridization of carbon in CX bond. Then instability of phenyl carbocation. So you have to explain this point. So this is a compulsory asked question. Why aryl halides are less reactive towards the nucleophilic substitution reaction. Is it clear? Yes. One
Yes,
more.
ma'am.
Yes. And one more point you can remember is that now this benzene. Do you know what is meaning of electrophile and what is the meaning of nucleophile? Electrophile and nucleophile. Yes. What do you mean by electrophile and what do you mean by a nucleophile? Electrophile is what? Electrophiles are electron deficient. Okay. Electron deficient. Electrophiles are electron deficient. Okay. Then what are nucleophiles? Nucleophiles are what? They are electron rich, right? Electron rich. Now, benzene. Benzene is what? Benzene is a electron rich. Now, electron rich, right? Species. Now, tell me, whenever like charges are there, like charges, what will happen to like charges? When you have two like charges, charges will repel each other, okay, and unlike charges will attract each other. Now, if you have two electron-rich species, suppose I have a benzene ring and I have a nucleophile. Is it possible for the reaction? Will the charges attract each other? No, right? It will not attract each other. There will be a repulsion. Okay, as the electron-rich species, it will approach this benzene ring. What will happen? It will repel, and thus the nucleophilic substitution is not possible. Okay, so these are some of the points, okay, which you have to list out when this type of question is asked. So this is another important question. So please mark this important question asked, okay, for 3 marks. Why aryl halides are less reactive towards the nucleophilic substitution reaction. Okay, so let me go for the next one. So, however, the aryl halides, okay, so they have the property of having electron withdrawing group. So, if they have, if on the benzene ring, okay, if the electron withdrawing groups like nitro group or SO3 groups are present at ortho and para position, then what it will go? It will undergo nucleophilic substitution reaction. Okay, suppose I have your NO2 group and your one NO2 group. So, if okay, if there is a presence of any NO2 group or any sulfuric group, okay, then at ortho or para position, then it will undergo nucleophilic substitution reaction. But only aryl halide cannot undergo nucleophilic substitution reaction. If there is a presence of any electron withdrawing group, okay, then it can undergo a nucleophilic substitution reaction. So this is a reaction. Okay, so this is a nitrochlorobenzene, okay, chloronitrobenzene, that is your NaOH, okay, and in the presence of 623 Kelvin and 300 atmospheric pressure and acidification, what you obtained is a, okay, nitrophenol. Okay, so these are the different reactions. So whenever there is a presence of any electron withdrawing group on the aryl halides, okay, at ortho and para position, then it will undergo a nucleophilic substitution reaction easily. Okay, now here you can see. So the presence, so as I have discussed you, so the presence of electron withdrawing groups, okay, like nitro group, what it will do? It will tend to increase the reactivity. So so these are the reaction. Okay, so the presence of nitro group, what will happen? What will this nitro group? How the reaction or how the reactivity increases? Okay, how the presence of this nitro group is increasing the reactivity. So here the nitro group is present at what? At the para position. So what is ortho position? These are the ortho positions. Okay, and this is a para position. This is a meta position. So this is ortho, this is meta, and this is a para position. With respect to this, this is your para position. Now, so whenever such nitro group, okay, whenever a nitro group, it is present at ortho or para position, what it will do? It will withdraw the electron density. It will withdraw. It will withdraw means it will withdraw the electron withdrawing. Withdrawing means it will take towards itself. So it will withdraw the electron density from the benzene ring, and what it will do? It will facilitate the attack. Okay, it will make the nucleophile attack on the haloarene. Okay, there will be a formation of carbon anion. What do you mean by carbon anion? Carbon anion means a negative charge. Okay, we have seen what is carbocation. Carbon anion means a negative charge. Okay, so when a benzene ring undergoes stabilization, you have seen. So there is a negative charge present, okay, on the benzene. So this is called as carbon anion, and this carbon anion is stabilized. How? It is stabilized through the resonance structures. Okay, it is stabilized to the resonance, and this negative charge, okay, thus apparently the negative charge, it will be appeared at the ortho or para position with respect to the halogen. So this is more stable. So what will happen with respect to the halogen if the substituent is stabilized by the nitro group? So so with respect to this negative charge, okay, then your nitro group will be more stabilized. So this increases your reactivity. Okay, so the presence of nitro group at meta position. If the nitro group is present at meta position, okay, it will not stabilize the negative charge. But if the nitro group is present at ortho and para position, so there the negative charge what is present, it can be stabilized, and thus it will increase the reactivity. Okay, so this is the presence of electron withdrawing group. So like this, the question is asked, okay, from applicative point of view, how the nitro group, okay, it increases the reactivity. So nitro group, so as the carbon ion is formed, so the carbon ion, the negative charge can be stabilized, okay, at ortho and para position with respect to the nitro group, and thus what will happen? At ortho and para position, the negative charge is more stabilized, and thus the reactivity increases. Okay, so at meta position, the negative charge is not stabilized. Okay, and thus the effect of your electron withdrawing group. Okay, how it increases the reactivity. Is it clear? So very important. Okay, so these concepts are very important. So they will be asked in form of the applicative type. Okay, it will be asked in the applicative type. Is it clear up to your? So next we are going to see the electrophilic substitution reactions. Okay, next is the electrophilic substitution reaction. So haloarenes. Okay, haloarenes, as we know, haloarenes, they undergo electrophilic substitution reaction in the benzene ring. Okay, so as the halogen atom is ortho and para substituted, as you know, the halogen, okay, the halogens, they are deactivating, but they are ortho and para directing. They will get linked at ortho or para direction. So thus the substitution always takes place at ortho and para substituted derivatives. So what we get, we obtain ortho and para substituted product. So let us, so these are also important. Okay, asked in point of exam, this what? Complete the following. So explain the halogenation reaction, explain nitration, so like that. So these are also important. Mark these important electrophilic substitution reactions. So first we are going to see the halogenation. Okay, halogenation reaction. So this is a halogenation reaction. So what is our starting product? The starting, this is chlorobenzene. So chlorobenzene, what we are going to do with chlorobenzene? We are going to react it with 2Cl2, take 2Cl2 in the presence of anhydrous FeCl3. Anhydrous FeCl3, what we obtain? We obtain 1,4 dichloro benzene. Okay, 1,4 dichlorobenzene and 1,2 dichlorobenzene. So ortho substituted product is a major product and para substituted product is a minor product, plus 2 HCl, plus 2 HCl. Why? Do you have a doubt why ortho is a minor product and why para is a major product? Yes. Do you know why it is so? Can you tell me, students? Okay. So why you say that ortho is minor and major, para is this? You can see that the atoms are close to each other, right? So there is a chance of steric hindrance, right? There is a steric hindrance. Steric hindrance means what? There is a bulky groups. Okay, both the chlorine atoms are bulky groups, and thus they are very close to each other. Okay. Now here you can see. Okay, here you can see the atoms are very far from each other. This is a major product and this is a minor product. Okay, remember this. Remember this, very important. So why this is a minor product? It is minor product due to the steric hindrance. Okay, it is due to steric hindrance. Okay, remember this. Fine. So this is a halogenation. Is it clear? So we'll go for the next one. Next is nitration. Next is what? Nitration. So let us do nitration. So again, we are going to take two. Okay, 2Cl. So that is chlorobenzene. So we are going to do the nitration on a chlorobenzene. So two molecules of chlorobenzene in the presence of concentrated H2SO4 and HNO3. Okay, what we get here, yes, in the presence of concentrated HNO3 and concentrated H2SO4, what we get? 1, 2, 1 chloro, okay, 1 chloro, 2 nitro benzene and 1 chloro, 4 nitro benzene. So again, here this is a minor product, this is a major product. Why? Because of steric hindrance, okay? Remember this. So this is a nitration. So nitrating agent. So from concentrated HNO3 and concentrated H2SO4, okay, what we obtained is our nitrophile is what? It is a NO2. Okay, NO2 is a electrophile. NO2 is a electrophile. And in halogenation, what was the electrophile? It was Cl plus. Okay, it was Cl plus. Is it clear? So this is a this is a electrophilic substitution reaction, that is a nitration. I hope. So what will be the again one product? It will be 2HCl. 2H2O. Okay, it is a 2H2O. Okay, it will be 2H2O. So this is the byproduct obtained. Is it clear? Yes. So we'll move for the next one. Next is sulfonation. Next is sulfonation. So again, 2-chlorobenzene. 2-chlorobenzene in the presence of concentrated H2SO4. So from H2SO4, what is the electrophile produced? It is SO3H. Okay, it is SO3H. So SO3H is the electrophile. You heat it. What you obtain? You obtain 2-chlorobenzene. Okay, 2-chlorobenzene sulfonic acid and 4-chlorobenzene sulfonic acid. So again, this is a minor product because of the steric hindrance, and this is a major product, plus 2H2O. Okay, plus 2H2O. So this is a sulfonation reaction. This is a sulfonation reaction. So what is the electrophile? It is a SO3H. Okay, SO3H gets attached at ortho and para position. So whenever we are undergoing the electrophilic substitution reaction, so these are more stable. Okay, so the benzene ring, the haloarenes, they undergo electrophilic substitution in the benzene ring because the halogen, okay, atoms is ortho and para directing. Okay, so the substitution takes place at ortho and para position itself. Okay, because you saw that the negative charge is more stabilized at ortho and para rather than your meta position. Okay, next one is Friedel-Crafts reaction. So one is alkylation, another is acylation. So what is Friedel-Crafts alkylation? Okay, first one is the alkylation. So two Cl, that is we take two molecules of chlorobenzene in the presence of alkyl halide. Okay, you take two CH3Cl, then anhydrous AlCl3. What you get? We get 1-chloro 2-methyl benzene and 1-chloro 4-methyl benzene. Again, this is a minor product and this is a major product. Okay, this is a minor product and this is a major product. So this is a Friedel-Crafts alkylation. Okay, this is a Friedel-Crafts alkylation. Okay. Next, we are going to see the Friedel-Crafts acylation. Okay. Next is Friedel-Crafts acylation. So in Friedel-Crafts acylation, same, we are going to take two moles of chlorobenzene. We are going to react it with a acetyl chloride. Okay. Yes. In alkylation, which is our electrophile? It is a CH3 plus. Okay. So our electrophile is generated from this CH3Cl, that is your methyl chloride. Okay. And your electrophile is CH3. So it gets attached at ortho and para position. And here in acetyl chloride. Okay. Acetyl chloride, what is our this is CH3 CO. Okay, CH3CO. So C double bond O. So this gets attached. Okay, so this get attached to your, so this is the electrophile. So this is the electrophile. Okay, so this is the electrophile. So chlorobenzene, it undergoes acylation in the presence of acetyl chloride. You can see your CH3Cl is there. Here there is only CO. So CH3COCl in the presence of anhydrous AlCl3. Okay, what is obtained? 2-chloroacetophenone and 4-chloroacetophenone. Okay, so this is a minor product and this is a major product. Okay, so these are the electrophilic substitution reaction. Is it clear? So very important electrophilic substitution reaction. So halogenation, we have seen halogenation, we have seen nitration, we have seen sulfonation, and we have seen Friedel-Crafts reaction, that is alkylation as well as acylation. Is it clear? Yes, up to your, is it clear? Any doubts up to your?
No, ma'am.
Okay, others, I hope everyone is understanding. So, okay, some things might be just moving. So, what you have to do? So, you have to just revise it. Okay, so every day, organic chemistry, first of all, it is a volatile subject. So, you have to keep studying it continuously. You have to practice the reactions. Okay, you have to write and write. Simply by seeing on the reactions, it will not go into your mind. So you have to just practice. You have to write the equations. You have to practice the equations. Okay, then only it will be fed in your mind. Okay, simply just by looking from above, it will not help you. So from now itself, you start practicing. Okay, so so these were some of the electrophilic substitution reactions. Okay. So next is the reactions with metals. Okay, so reactions with metals. So we are going to see the Woods-Fittig reaction. We are going to see the Woods-Fittig reaction. Now, what is Woods-Fittig reaction? Okay, we are going to take Woods-Fittig reaction. So in Woods-Fittig reaction, important, mark this as important for 2 marks. Important for 2 marks. Okay, so a mixture of, one is a alkyl halide. So you are going to take a mixture of a alkyl halide. Okay, and we are going to take and one aryl halide. So a mixture of alkyl halide and one aryl halide, we are going to react it with a active metal like sodium. Okay, a metal like sodium. And what is going to form? We are going to form a alkyl aryl, alkyl aryl. Okay, or you can say alkyl arenes. Alkyl, it will give you alkyl arenes. Okay, you will obtain a alkyl arenes as the product. So this is the Woods-Fittig reaction. This is what Woods-Fittig reaction. In Woods reaction, what we have seen, we have taken two alkyl halides. Okay, two alkyl halides. We react it with sodium. What you obtain? We obtain R and R plus 2NaX. So this was what? In the presence of dry ether. This is your Woods reaction. Right? Two alkyl halide reacted with active metal like sodium. You alkanes, higher alkanes are obtained. Right? So this is a Woods reaction. Now, Woods-Fittig is what? Woods-Fittig is what? One is a alkyl halide, another is a aryl halide. Okay, and we are going to react it with the sodium in the presence of dry ether. What is obtained is we are going to obtain a alkyl arene. Okay, plus 2NaX. So this is what? This is a Woods-Fittig reaction. This is a Woods-Fittig reaction. Okay. Then one more Fittig reaction. Next is a Fittig reaction. So what is Fittig reaction now? Let me write here. Okay, let me summarize it here itself. Okay, now Fittig reaction. So I've written it here. Okay. So Fittig reaction. In Fittig reaction, we are going to take two aryl halides. We are going to take what? Two aryl halides. We react it with sodium 2Na. Okay, in the presence of dry ether. What we are going to get? We are going to get plus 2NaX. Is it clear? So this is a Fittig reaction. What we are going to get? We are going to get a aryl groups. Okay, two aryl groups are joined. Right. So this is a Fittig reaction. This is a Woods reaction, and this is a Wood-Fittig reaction. So in Woods reaction, we are going to take two alkyl halides, and in Fittig reaction, we are going to take two aryl halides. And in Woods-Fittig reaction, we are going to take one aryl and one alkyl group. Is it clear? So examples, we'll see the, just a second, I'll write the examples also. You give me the, okay, so this is the same. So let me give you So let us see first the Woods-Fittig reaction. Okay, Woods-Fittig. So for Woods-Fittig, let me give you Woods-Fittig. Okay, CH3Cl plus plus. Okay, let me write it here. It's a 2Na plus. Okay. Then in the presence of dry ether. Okay, give me the answer. And next one I'll write. So here. Okay. So this will be a product. So what it will be? One will be your 2. What will be the byproduct? It will be 2 NaCl. Okay. And CH3. Right. So this is what? This is a Woods-Fittig reaction. So one alkyl halide and one aryl halide. Okay. You get a alkyl arene. And here, what will be the product?
2NaCl.
Yes. And a biphenyl. Okay, it is called as a biphenyl. Two benzene ring are getting fused. Okay, so this two benzene ring will get fused. So these are the biphenyl, or it is called as diphenyl. Diphenyl. Okay, so this is a Fittig reaction. Is it clear? So all three important: Woods reaction, Fittig reaction, and Woods-Fittig reaction. Very important name reaction. Okay, so mark these all as very important for 2 marks. Is it clear up to here? Yes. Is it clear?
Yes, ma'am.
Okay, so we have completed the reactions of uh, haloarenes. Okay, so the remaining things we will be discussing in the next class. So if you have any doubts regarding today's session, you can ask. Yes, any doubts regarding today's session? Okay, fine. So I shall end the session here. Yes. So we'll meet in the next class. Thank you.